All of calculus is based on the idea of a limit. In this video, we will look at two related problems that require limits. The first problem is finding the slope of a line that is tangent to a curve. And the second problem is finding the instantaneous velocity of a moving object. Let's look at example 1. The points P 0.5, 2 and Q, x, y are on the graph of the function f of x equals 1 over x. Complete the table below. The y-coordinate of Q, the point Q of xy, and the slope of the secant line passing through the points PQ. Round your answer to 4 decimal places where necessary. Let's start off by looking at this graphically. Here we have the graph of f of x in blue, f of x equals 1 over x. And we have the point P at 1/2, 2. And we also have this red line, which is the tangent line to f of x at the point P. Normally, when finding the slope of a line, we need 2 points. But this tangent line has only one known point at 0.5, 2. So what this problem asks us to do is to take a series of points that get progressively closer to the point P. So, for example, we could start with x equaling 1, and we have this point Q when x is 1. When x is 1, y is also 1. And the point Q of xy is 1, 1. Next, we want to find the slope of the secant line that goes through PQ. In other words, we want to find the slope of this line. Well, if we have the point P, and now we have the point Q here, we should be able to find the slope pretty easily. The difference of the y's in the numerator and the difference of the x's in the denominator. And as you'll see here in green, we have that the slope is indeed -2. Now we're going to repeat this process for x values getting progressively closer to 0.5. So first we're going to try x equals 0.9. If I take my point Q and move it so we are at x equals 0.9, we now have this line here. And I've got GeoGebra here already doing all the calculations for us. So we can see that Q has a y value of 1.1111, giving us the point 0.9, 1.1111, and then the slope is given to us here on GeoGebra as well, -2.2222. And so what's going to happen is we're going to continue like this, choosing x values closer and closer. And the picture you want in your head as Q climbs up that curve is you want to notice that the slopes of your green lines get progressively closer to the slope of the red line, which is what we're trying to find. And that is the idea of a limit. Let's go ahead and switch to a calculator to help us find the values for each of these columns. First of all, to get the y value, we simply plug in the x value into our function f of x. So f of x is 1 over our x value. Our next x value is 0.8. And there we have 1.25 is going to be our next y value. So our next point Q is at 0.8, 1.25. And now we need to go ahead and find the slope of that secant line. So we're going to take the y value at P and subtract off the y value we just found, 1.25. And we're going to divide that by the x value at P, which is 0.5, minus the x value that we're using for this particular Q point, which is 0.8. And we get -2.5. One thing you can do on Desmos here is right here, you can actually put ANS for answer, and it'll automatically take the answer from the previous line. So if I go ahead now and change this to 0.7, and change this to 0.7, I've now found the slope for the next row. Now we can repeat the process for 0.6. (0.55), and finally 0.51. So now we're going to look at this column of values and decide if we think that these numbers are approaching a specific number. And if you're not totally convinced, you can choose values even closer to 0.5 for x. In other words, we can come over here, instead of 0.51, maybe put 0.50001, and then do the same thing here, 0.50001. And if you now look over here at your slope, it sure looks like we're approaching -4. So the question now wants us to use the values from that last column of the table to guess the value of the slope of the line tangent to f of x at x equals 0.5. And our guess is going to be a slope m, I'm going to put sub tan for the slope of the tangent, equaling -4. Finally, they want us to use this guess to find the equation of the tangent line. And all we're going to do is use this known point for our tangent line and the slope that we guessed. So that gives us y minus 2, the y value from point P, equaling the slope, -4, times x minus 1/2. That is the x value from point P. Distributing, we get -4x plus 2. Adding over the 2, we get y equals -4x plus 4. If we take one last look at our figure in GeoGebra and maybe zoom in a little bit, we can see, first of all, that our equation of the tangent line was indeed y equals -4x plus 4, as you see here in red. But you can also see that those green secant lines, their slopes approach the slope of the red line, the tangent line, as our x's get closer and closer to 1/2. That's the idea of a limit. Let's look at the next example. Example 2, if a ball is thrown into the air with a velocity of 40 feet per second, its height after t seconds is given by y equals 40t minus 16t squared. Round your answer to 4 decimal places where necessary. Find the average velocity for the time period beginning at t equals 2 seconds and lasting 0.5 seconds, 0.1 seconds, 0.05 seconds, and 0.01 seconds. Finally, they want us to find the instantaneous velocity when t equals 2. First of all, let's make sure we understand what's going on here. So t is representing time after the ball is thrown into the air, and y is telling us how high the ball is. So when t equals 2, we have the height is going to be y equals 40 times 2 minus 16 times 2 squared, which gives us 80 minus 16 times 4, which is 64, which is 16 feet. So if we think about the problem we had in example 1, we can think of this as point P equaling 2 for our input. Instead of x in the last problem, it's now t for time, and y is our output, the height that the ball is above the ground. From there, we're being asked to find the average velocity 0.5 seconds later, 0.1 seconds later, and so on. So we want to build a table where we have t values and y values. So we're going to start with our 2 seconds and then add 0.5 to get 2.5 seconds, and then 2.1, 2.05, and 2.01. And we can plug in each of these t values into our function to find the height. For example, y equals 40 times 2.5 minus 16 times 2.5 squared. You can go ahead and pause the video and work this out for yourself. I got 0. And then here we'll get y equals 40 times 2.1 minus 16 times 2.1 squared. In this case, I got 13.44, and continue in the same way down here. Next, we want to find the average velocity at each of these points in time. Let's take a look at the graph to see how this works. So here again, we have our function in blue, f of x equals 40x minus 16x squared. Remember, for this problem, instead of x's, we're using t's. And you'll notice that we have a tangent line again at the point P, which is at 2, 16. Now, in the problem, it tells us that velocity is measured in feet per second, feet over seconds. And here we have our y values being feet. So think of your vertical axis as representing feet, and your horizontal axis, the t-axis, is representing time. So if we are finding velocity as feet over time, right, feet per second, then we can think of velocity as simply rise, change in y, over run, change in t. So we just need slopes. So we're going to introduce point Q, and that first point was down here at 2.5, 0. And we want to find the slope of this secant line. And then we'll continue successively with points Q getting closer and closer to point P, and the slopes of the green lines, which represent average velocity over the time change between P and Q. Those velocities, those slopes, should approach the instantaneous velocity, which is the slope of our tangent line. So just as before, to find the slope of our secant lines, we're going to take the difference in the y's. So I'm going to take the y value from our point P, which is 16, minus our y value from this point Q here, which is 0, and then get the difference between the t values, 2 minus 2.5. When we do that, we get 16 over negative 1/2, which is negative 32. That is the average velocity in feet per second between the times t equals 2 seconds and t equals 2.5 seconds. We now repeat this for the rest of the values. Go ahead and pause the video, do that on your own, and I'll go ahead and fill in those values in a moment. Finally, we're going to guess the instantaneous velocity by again looking at this last column and noticing that our values seem to be approaching maybe negative 24. Now that might seem a little imprecise, just guessing that it's negative 24 feet per second. But for now, that's good enough. Later on in this class, we'll learn techniques to find the instantaneous velocity exactly every time. Go ahead and do problems 1 through 4 on your own.